Oh my goodness. What did you do, Tom? What did you do, Tom?
Thousands of handwritten digit images, each one labeled with the numbers that they're supposed
Me
to
right
be.
now.
And as provocative as it is to describe a machine as learning, once you actually see how it works, it feels a lot less like some crazy sci-fi premise, and a lot more like, well, a calculus exercise. I mean, basically it comes down to finding the minimum of a certain function. Remember, conceptually, we're thinking of each neuron as being connected to all the neurons in the previous layer. And the weights in the weighted sum defining its activation are kind of like the strengths of those connections. And the bias is some indication of whether that neuron tends to be active or inactive. And to start things off, we're just going to initialize all of those weights and biases totally randomly. Needless to say, this network is going to perform pretty
So again, my brain is
going
to do what this thing does on an 8-bit clock. Okay,
for example,
I want to be able to slow this down.
And the output layer, it just looks like a mess.
One move.
So what you do is you define a cost function.
Wrong. Here, but it's 0 wrong on an 8-bit clock. It's 1 wrong. It's 2 wrong. And if it is 2 wrong, when I reset the clock to the 8-bit thing to feeds and speeds turn back over on a reset of an Arduino, I got 1s and 0s traveling through breadboard. Hook my balls up to this and be a conductor.
And the value that you want them to have. And this is what we'll call the cost of a single training example. Notice, this sum is small when the network confidently classifies the image correctly, but it's large when the network seems like it doesn't really know what it's doing. So then what you do is consider the average cost over all of the tens of thousands of training examples at your disposal.
So if I'm hitting the reset or the move button, I got a pin chip to do things move. 1, 2, 3, 4, it does 1. I can turn down the timelines on those things to make it do those things before this thing just goes spitting out codes, 1s and 0s, X down.
And spits out 10 numbers as its output. And
10 numbers is output.
Parameterized by all these weights and biases.
X was 10
numbers. The cost
numbers.
function is a layer of complexity on top of
what
that.
were those 10 numbers? Treadline, training people, forklift standards, chemical analysis report, general relativity, Schrodinger's equation, Heisenberg's uncertainty.
And the way it's defined depends on the network's behavior over
3 blue,
all
1
the
brown
tens
coming
of
in here in the
thousands
middle
of
that day.
pieces of
That could have
training
been the
data.
number.
That's a lot to think about. But just telling the computer what a crappy job it's doing isn't very helpful. You want to tell it how to change those weights and biases so that it gets better. To make it easier, rather than struggling to imagine a function with 13,000 inputs, just imagine a simple function that has 1 number as an input and 1 number as an output. How do you find an input that minimizes the value of this function? Calculus students will know that you can sometimes figure out that minimum explicitly.
If I did that,
that's not always feasible.
And I got
really
more than 51% across the board.
Certainly not in the 13,000
half you across the room were like, boo, and the other half were like this, and I was like this, and I could actually count how many of you there were.
The more flexible tactic is to start at any old input.
You're right, I got that big one over there, and most of this are the grannies inside here.
Specifically, if you can figure out the slope of the function where you are,
interesting.
Then shift to the left if that slope is positive, and shift the